Hello, it's Dr. C, and I want to talk to you today about thread synchronization. Now, it turns out that thread synchronization is the second dimension of threading and threading interaction. The first is threads as independent workers, which provide very little in terms of problems for us. However, when threads share data, and remember, threads are part of the same process space, so they have access to all the data elements that are part of a process, or part of a program. So when threads potentially can access the same data, we run into potential problems, and that's what thread sharing and synchronization is all about. For example, we may have multiple threads operating on an airline reservation system. Remember, there's only one occurrence of the code, with multiple threads coming into the code at their own pace, leaving the code, keeping track of where they are within the code. So you might have reservation agent 1 taking a reservation, telling the customer, yes, I've got this free seat for you, and concurrently another reservation thread seeing that same free seat, assigning both customers the same free seat, and of course when they get on the plane there's some kind of conflict. So how can we solve that problem? Well, the solution is to put a lock on the code. Now, this is a little bit different from the database world, where we can put locks on the data which prevent multiple processes from accessing that data. It's the same basic principle, but here in Java, the way the Java threading system works, we put a lock on code, allowing only one thread at a time to get into that code. So if we can put a lock on the code, the first thread in grabs the lock, puts the lock on the code, gets the seat, assigns it to the customer, leaves, releases the lock, and then when other threads show up, they find that that seat is taken. Now in Java, we implement this lock behavior through a keyword called synchronized. So we can assign to any method in any class the keyword synchronized. When we do this, the implication is when a thread makes a call to that method, that once a thread starts executing any code of that method, that code is then locked to any other threads that may come in. So if another thread is executing code and says, all right, let me execute this same method, the second thread on the scene is no longer runnable, moves over to the non-runnable state, and is not available for execution by the CPU. And all other threads that come along, while that first thread has access to the code, all the other threads that come along and try to execute that code will be blocked until the first thread finishes. In this way, we can prevent problems with multiple threads accessing data at the same time. The problem is not with multiple threads reading data at the same time, it's with multiple threads changing data concurrently. So here we see a Java class called account. It's got a balance, and notice that we have synchronized both the getBalance method and the deposit method. Now, what this really means is the first thread in any one of those methods actually grabs the lock and locks other threads out of both of those methods. Because the way the lock mechanism works is the lock is associated with each object. So each object has a lock, and when a thread enters a synchronized method of an object instance, other threads are prevented from executing any of the synchronized methods of that object instance. So we can see this in this example of the synchronized getBalance method. Now the class, when you look at the class, you will see the synchronized method. But remember, this is not a static method. So every instance, every object instance will have a getBalance method, because every object instance will have instance data that getBalance method will be accessing. And so, very important the object instance is locked. Not the method itself in any shape or form, but the method with respect to an object instance. Because remember, every instance has its own lock. So if I have an object, I have an account A1 and another account A2, if a thread is going into accounts A1 get balance method, then that object or that thread has the lock on that object. But another thread could come along and execute code in account A2 with no problem. And here we see a diagram illustrating that. We have a thread, we have two threads actually, both are trying to execute code on this object A. One thread is going to be trying to execute the method foo, another thread is going to be trying to execute the method bar. Both of these methods are going to be associated with this object instance. So here we see the first thread enters the method foo and now has control of that object. The second thread T2 that tries to execute bar is prevented from doing so because the first thread is still executing within foo. And here we see our T1 thread is still in foo. Any other threads that come along trying to execute either foo or bar, part of that object, are going to be blocked. Now, if a method is not synchronized, then any number of threads can come in and start executing code for that particular method. So down here we see the little blue thread guy is in the method BOZ, but BOZ is not synchronized. So again, the key takeaway is that in Java, objects have locks. The locks are acquired by threads whenever they enter a synchronized method of that object instance. So let's stop and take a look at what can happen when you have more than one thread active and accessing the same underlying piece of data. So we're going to look at a race condition in action. But to do that, we want to set up a Java class. It's a class called counter, and it's a very simple class. It keeps track of an internal instance variable C, the counter, and has a public method increment, which simply increments the counter when it's called, and a method called decrement that simply decrements the counter when called, and a method value that gives us back the value of C, our counter. And down here I've got a little main program where you can see on line 20 we actually create an instance of the counter and then we create a couple of thread worker classes. So let's look at our thread workers. The thread worker class is going to extend thread, so right away we know to look for a run method, which is down here. But let's see how thread worker is set up. I actually have a constructor called thread worker, and so what we want the thread worker to do is increment, as you can see down here. We want the thread worker to increment our counter some number of times. So one of the problems we've got to solve is how do we get the thread worker to know about the existence of the counter. And so we have our constructor here where we pass in two parameters. One, a reference to some counter that our thread is going to access, and then some variable which is going to be the number of times that we want that increment to take place. So when we construct this thread worker instance, we're passing in a reference to counter. He remembers the value of counter, stores it in a variable C, and then down in the run method can actually do the increment. And so this loop is going to occur some number of times depending on the parameter. So let's go back to our counter main program, and this main program can be anywhere Doesn't have to be in the counter class. It can be any class that I have in my package here. And so we see we create our new counter, and now this is the reference to the counter, CC, and we use that CC, we pass it to two instances of thread worker. So we've got thread worker 1 and 2. So they both get a reference to the counter. We're going to ask them to increment the counter 10,000 times each. Then down here on line 26, we launch our threads, TW1, TW2, start both of those guys up. And then we now have 3 threads executing, or at least potentially executing, thread T1, T2, and the main application thread that main is running in. So what we want is we want to have the main application thread wait around for the 2 threads to complete. So we do a join here. So in effect, the way you interpret this is the main application thread says to TW1, I want to join you when you're finished, when you're completed, when you're dead, when your run method terminates. And we're going to do the same thing for thread 2. So this little construction here guarantees that the main execution thread will not terminate until the other 2 threads have completed their work. And then, of course, since the main thread will now move out of the runnable pool, it could potentially be interrupted by another thread, but it's not in this program. But we need to make sure the compiler will make sure that we deal with that interrupted exception through a try-catch block. And so then we wake up and we print out the value of the counter is CC value. Well, if we have 2 threads, each incrementing the counter 10,000 times, then the value should be 20,000. So let's run this and we'll see what the answer is going to be. Let me move this over here. Let's see, move the window around a little bit. Let's see. Alright, I'm going to take that. I'm going to run this again, do Shift F6 in NetBeans. And there we have the value of the counter, 20,000. So that's great. We're ready to go. Publish the program, send it to our banking colleagues, and we'll run it again. Okay, run it again. Looks good. 20,000. Looks great. Let's run it again. 20,000. All right, looking good. Run it again. 20,000. Looks good. Looks good. Keep running. What's going on here? Value of the counter, 19,998. We have been shortchanged 2 values in the counter. Run it again. 20,000. 20,000. 19,994. So you see about 1 out of 6 or 7 times the answer is incorrect. So this is not a thread-safe program. Even though our counter class looks so simple, it is not thread-safe. And it's not thread-safe because multiple threads, when 2 threads come in and execute this code concurrently, we can have a race condition. What you have to realize is that C++, even though it looks like 1 statement, is actually 3 statements at least behind the scenes. One is, let me fetch the current value of C, put it into some temporary location, let me increment that temporary location, let me take that value in the temporary location and put it back into the position of counter in memory. Because remember, these arithmetic operations are done in registers in the CPU, fetching values from memory. So what's happened here is the reason we get this incorrect value is because one thread is told to execute increment. It fetches the current value of C from memory, stores it in its own local variable space, and then is interrupted. And the second thread comes in, executes the increment method, grabs the value of C out of memory, so they're grabbing the same value of C. They're both incrementing C, and then they're returning their values back into C. So when that interruption occurs, when that sequence of behaviors occurs, we're going to get an incorrect value. So our code is not thread safe. What we want to do is we want to guarantee that when one thread executes increment, that it is able to complete the increment without being interrupted by another thread that comes along. And so in Java, what we can do is make use of the synchronized keyword. We can put synchronized there, and we should put synchronized, synchronized there, and this will now mean that a thread will, once it gets the lock associated with this counter object, it's going to be free to complete the code that makes up C++ without being interrupted in its process by the other thread. So we'll just rerun this now with the synchronized method, and so here we see 20,000, and we'll keep running it, and as long as we keep running, we're going to be getting 20,000 because we've now synchronized the code. If I take off the synchronized here, which is where the action is, got one synchronized method, but we're not protecting increment. There we go, 19,998. So you see the dangers of multi-threading, and very simple code is not by definition thread safe, and the problem is because the threads are concurrently trying to access the same piece of data, which is variable C. Now you might think, well, you're protecting the code, what about protecting the data? What about variables? Well, variables themselves cannot be synchronized, but the object model is you keep your data variables private, and you access them with accessor methods. So that's the way you control access to data. In fact, that's why synchronized methods exist anyway, because you're trying to control access to data. If there were no data, we wouldn't have to worry about synchronization. Because what the potential problem here with your data is, remember, even though we're looking at these programs as a single line, for example, balance plus equal amount, so we're adding amount to the balance variable, even though that appears as one line, when we think about it from a lower machine level language, the thread is taking the current balance out of a register, storing it in a temporary location, adding the amount to that temporary storage location, and then taking the value in that storage location and putting it back into the balance location. So that's, you think about it as a three-step process. If two threads come in, each of which grabs the balance and adds something to it, then the result is not going to be correct, because they'll both be starting from the same balance amount, and one will return balance plus 10, another will return balance plus 30, but the values will overwrite each other. So that's why it's important that we control access to data until the thread finishes its work, so we don't get this interleaving of incorrect values. In addition to synchronized methods, you can create a synchronized block within a method. And the reason you would want to do this is because if you throw synchronized methods all over the place, then you are really affecting the performance of your program, because you may have a lot of threads in your program, but they're all going to be waiting around waiting for these locks to be released. So if you, for example, have a method that has a lot of code in it that's not related to the data access, the potential problem of accessing some shared piece of data, then you can fine-grain your locking and your synchronization by introducing a synchronized block. And when you put a synchronized block in, it's only when a thread hits that synchronized block, in order to execute it, it needs to grab the lock on some object. So a synchronized block has as its parameter some object that serves as the lock. So sometimes people write programs that create objects to serve for no other purpose than to be sort of a lock object. And so the thread that sort of owns that lock object can enter the synchronized block. Other threads that come along and enter synchronized statements anywhere else in a program that use that same lock will then be prevented from accessing the code until the first object has completed its work. So synchronized blocks are a really more advanced notion in the world of synchronization, but you need to know that they're out there and available to you. So in this example, we see the use of a synchronized block within this method called abs for absolute value. So what this method is doing is they're passing in an array of integers, and the job of the abs function is to turn any negative values into positive values. Now, if you're in a multi-threaded environment, you're manipulating an array. While you're manipulating the array, you don't want other threads to come along and start changing the values while you're in the middle of changing values. Just remember, your thread can be interrupted at any time unpredictably, and another thread can come in and start doing work. So we could have set this up as a complete static method, but this example just is to show you how a synchronized block could work. Of course, the synchronized block requires some object to use for the lock. So in this case, we simply use the array. There are objects all over the place in Java, and an array is certainly an object. And so we synchronize on the array. So in order for this absolute value iteration to occur, the thread executing this code must own the lock on the values object. Now, when the thread finishes this loop, then it drops outside the synchronized block area, and then the lock is available for other threads to come along and do their work. But it's just another example of the synchronized block in action. So to summarize, we control access to data on threads through synchronization, either a synchronized method that's defined as part of a class, or through synchronized blocks. Either way, the thread grabs the lock and prevents other threads from accessing that object. And so this allows multiple threads to act concurrently in the context of shared data without interfering with each other, creating potential problems, incorrectness of the data values. And so synchronization, which actually comes out of the operating system world, and the whole process world uses synchronization to lock various things in the operating system. We now see this incorporated into the Java programming language because working with threads is now becoming an important part of the application development world.